In recent years, technologies for building AI agents, such as OpenAI Agents SDK, Claude Agent SDK, AutoGen, and LangGraph, have evolved rapidly. Multiple agents can now bring their own specialized capabilities and collaborate with one another to accomplish complex tasks. Multi-agent systems are reaching the point where they can be applied to real-world business operations. However, as agents become more capable and increasingly autonomous, a new set of questions begins to emerge. Who makes the final decision? Who authorizes execution? And when something goes wrong, who is accountable? This is where the concept of a Runtime OS comes into play. But is Runtime OS simply another new agent framework? Does it compete with OpenAI, Anthropic, AutoGen, or LangGraph? To answer that, let's first look at the fundamental difference between them. The conclusion is clear. Runtime OS is not another agent framework. What OpenAI Agents SDK, Claude Agent SDK, AutoGen, LangGraph, and similar frameworks excel at is building capable agents, coordinating multiple agents, planning tasks, and using tools to execute them. In other words, they provide the mechanisms for how agents operate and execute tasks. Runtime OS, on the other hand, addresses a layer above that. When an agent proposes, "I want to execute this action," Runtime OS does not simply allow it to proceed. Instead, it determines who has the authority to make that decision, whether the action complies with organizational policies and boundaries, and whether human approval is required. Only authorized decisions are allowed to proceed to execution, and the entire process, from decision-making through execution, is recorded as a decision trace. So, if agent frameworks are designed to expand what agents can do, Runtime OS governs what may be executed, under whose authority, and within what boundaries. This means the two are not competing technologies. Agent frameworks provide agent capabilities and execution, while Runtime OS governs decision, authority, policy, human gate, and trace from a higher layer. So, when we look at the overall system architecture, where exactly does Runtime OS fit? This diagram shows how Runtime OS relates to existing agent platforms and frameworks. The key point is that Runtime OS is not designed to replace OpenAI, Claude, AutoGen, LangGraph, or other agent technologies. Instead, it works above them as a governance layer, taking advantage of their capabilities while controlling how those capabilities are used. At the bottom, we have the infrastructure, data, and tools layer, including databases, cloud platforms, APIs, enterprise systems, and IoT devices. Above that are agent runtimes such as OpenAI Agents SDK, Claude Agent SDK, AutoGen, and LangGraph. These platforms handle agent reasoning, planning, coordination, and tool execution. And above them sits Runtime OS, governing decision, authority, policy, human gate, permit, and trace. Runtime OS does not receive signals only from AI agents. Requests from people, events from enterprise systems, and detections from sensors or IoT devices can all be treated as signals. For each signal, Runtime OS evaluates who has the authority to make the decision, whether the proposed action complies with organizational policies and boundaries, and whether human judgment is required. If execution is approved, Runtime OS issues a command permit, allowing only authorized decisions to proceed to execution. The entire decision and execution process is then recorded in the decision trace ledger. This makes it possible to audit and explain, after the fact, who made a decision and why it was made. So, Runtime OS is not a mechanism for making agents more intelligent. It is a decision runtime and governance layer that enables organizations to take advantage of powerful agent capabilities while keeping their actions governed by human and organizational rules. To make this division of responsibilities even clearer, let's first look at the problems that existing agent frameworks are designed to solve. The central problem that agent frameworks are designed to solve is how to enable AI agents to perform complex tasks autonomously and efficiently. Let's look at a typical agent workflow. First, plan. The agent understands the objective, breaks it down into tasks, and creates an execution plan. Next comes tool. The agent uses the tools it needs, such as web search, databases, APIs, file operations, and code execution, to carry out the task. In a multi-agent system, handoff also plays an important role. Work can be passed from a research agent to an analysis agent, and then to a content creation agent, allowing each agent to contribute its own specialized capabilities. Finally, the agent evaluates the result and, if necessary, returns to the plan stage. Through this continuous loop of plan, tool, handoff, and result, agents can autonomously carry out increasingly complex workflows. To support this process, agent frameworks provide mechanisms such as delegation, tool loops, state management, workflow, and observability. This is precisely where OpenAI Agents SDK, Claude Agent SDK, AutoGen, and LangGraph are particularly powerful. But there is another problem that these capabilities alone do not solve. An agent being able to execute an action is not the same as an organization deciding that the agent is allowed to execute it. Who has the authority to finalize the decision? How far does the agent's execution authority extend? Is human approval required? And who is accountable for the outcome once the action has been executed? As agents become more capable and autonomous, these questions become increasingly important. Bridging this gap between can do and may do, that is the role of Runtime OS. So, what exactly does Runtime OS do? At its core is a sequence of stages: signal, decision, permit, execution, and trace. First, an AI or agent proposes an action, but at this stage, it is not yet a decision. No matter how confident the agent may be, its output is initially treated as a signal, a proposal or input for decision making. Next, Runtime OS evaluates that signal against organizational policy, authority, and boundaries. Who is authorized to make the decision? What can be executed? And under what conditions? And is human approval required? When necessary, the process passes through a human gate, and only then is the proposal finalized as an organizational decision. Runtime OS then issues a permit based on that decision. The permit defines conditions such as the authorized target, operation, scope, and expiration. Agents and enterprise systems are allowed to execute actions only within those defined limits. If an action attempts to cross those boundaries, the system fails closed and stops execution. Finally, the entire process, from signal through execution, is recorded as a trace. This makes it possible to audit and explain the reasoning behind the decision, the authority under which it was made, and what was actually executed. So, Runtime OS is not simply managing agent execution. It transforms proposals into decisions, connects those decisions to controlled execution, and makes the entire process accountable and explainable. At this point, we can express the fundamental difference between agent frameworks and Runtime OS more clearly. It is the difference between designing around an agent run and designing around a decision life cycle. This is the fundamental difference between an agent framework and Runtime OS. At the center of an agent framework is essentially the agent run. When an agent is given a task, it moves through the process by choosing among act, ask, and stop, depending on the situation. If it can proceed, it acts. If it needs more information or a decision, it asks. And if the task is complete, or if it determines that it cannot continue, it stops. Throughout this process, the agent uses tools, delegates work to other agents, receives feedback, and continuously optimizes execution. The central question here is, did the agent complete the task accurately and efficiently? Runtime OS, on the other hand, is not centered on the agent run. It is centered on the decision life cycle. Who has the authority to turn a signal into a decision? What authority and policy is that decision based on? How far should execution be permitted? And how should the decision and its execution be recorded as a trace? Runtime OS manages the entire life cycle of signal, decision, permit, execution, and trace. This also means that the two systems are evaluated from different perspectives. For an agent framework, the primary question is, was the task executed successfully? Runtime OS goes further and asks, were the decision and execution carried out under the correct authority and rules? And can we explain why? In other words, agent frameworks pursue execution optimization. Runtime OS pursues decision quality and governance integrity. However, this is not a question of which one is better. They are designed to solve fundamentally different problems. So, let's compare those differences more concretely through design elements such as authority, human gate, and trace. Here, let's compare agent SDKs and agent frameworks with Runtime OS from 4 key perspectives. First, their primary objective. Agent frameworks focus on maximizing the capabilities of LLMs and agents, planning and decomposing tasks, using tools, coordinating with other agents, and ultimately producing results. The central question is, how can the task be executed effectively? Runtime OS, on the other hand, focuses on governing decisions and making accountability explicit. Its central questions are, what should be permitted, what should be stopped, and who is accountable. The second perspective is authority. In an agent framework, each agent operates autonomously within the context and tools it has been given. Runtime OS explicitly manages decision authority based on organizational policies and boundaries. In other words, the ability of an agent to generate a signal is separate from the authority to finalize that signal as an organizational decision. The third perspective is the human gate. Agent frameworks can also incorporate human-in-the-loop mechanisms and approval steps. But in Runtime OS, the human gate is not simply an optional step within a workflow. It is treated as a governance control point based on authority, risk, and boundaries. And the fourth perspective is trace. In agent frameworks, traces are primarily used for observing agent behavior, debugging, and improving performance. Runtime OS goes further by recording the relationship between decision, permit, and execution, creating an evidence foundation for accountability, auditing, and traceability. So, agent frameworks address the question, how do we make effective use of AI capabilities? Runtime OS addresses a different question. What are those capabilities allowed to be used for? And who is accountable for the resulting decisions and executions? That is why these two approaches are not competitors. They are complementary. So, what does an actual system architecture look like when we bring these two complementary layers together? This diagram shows how the division of responsibilities we have discussed can be implemented as an actual system architecture. The important point is that OpenAI Agents SDK, Claude Agent SDK, AutoGen, LangGraph, and other agent frameworks are not replaced by Runtime OS. Existing agent frameworks continue to operate as the operational layer. First, Runtime OS evaluates policy, authority, and boundaries, and when necessary, passes the process through a human gate before finalizing the decision. If execution is approved, Runtime OS issues a command permit. The agent orchestrator receives that permit and handles planning, coordination, tool usage, handoffs, state management, and the actual execution of the task. In other words, there is a clear division of responsibilities. Runtime OS governs what is allowed to be executed, while the agent framework determines how it should be executed. Agents then connect through a gateway or adapter layer to APIs, RAG systems, external services, and internal enterprise systems. Beyond that layer are enterprise systems such as ERP, CRM, SCM, and MES, along with various data sources and the people involved in approval and execution. Now, let's follow the actual flow. First, a signal is generated by an AI, an agent, a person, or an enterprise system. Runtime OS evaluates that signal, finalizes the decision, and issues a permit if execution is authorized. The agent orchestrator then uses the necessary agents and tools to perform the task within the scope defined by that permit. Through the gateway, it interacts with enterprise systems and data, and the resulting information is returned to Runtime OS. The entire sequence of decisions and executions is then recorded as a trace. With this architecture, even when new agent frameworks emerge in the future, the operational layer can be replaced or extended while preserving the governance mechanisms above it: decision authority, policy, human gate, and trace. In other words, we can separate the evolution of agent technology from organizational governance. But this raises a new question. How do we evaluate whether a system built around Runtime OS is actually functioning correctly? The reality is that today's widely used agent benchmarks alone are not sufficient to answer that question. Today, a wide range of benchmarks have been proposed for evaluating AI agents. Some representative examples include Gaia, Agent Bench, OS World, and Agent Safety Bench. These are extremely important benchmarks, but they primarily evaluate two broad dimensions. The first is capability. In other words, what can the agent actually do? Can it reason effectively? Can it plan? Can it use tools correctly? Can it complete complex tasks from beginning to end? Benchmarks such as Gaia, Agent Bench, and OS World evaluate these kinds of agent capabilities from different perspectives. The second dimension is safety. Can the agent avoid dangerous actions? Can it prevent policy violations? Can it suppress harmful behavior? Benchmarks such as Agent Safety Bench represent important efforts to evaluate these aspects of AI agent safety. However, from the perspective of Runtime OS, capability and safety alone are not enough. Suppose an agent has extremely strong capabilities and successfully completes a task in a safe manner. Even then, several important questions remain. Who finalized the decision? Was the action executed under the correct authority? Did the required human gate function correctly? Can we trace the reasoning and process behind the execution afterward? And when something went wrong, was the system actually able to stop the execution? These questions cannot be adequately evaluated through capability or safety scores alone. If AI agents are going to participate in real decisions and executions within enterprises and society, we also need to evaluate governance, accountability, and traceability. That means Runtime OS requires a different set of evaluation dimensions from conventional agent benchmarks. So, let's define what those evaluation dimensions should look like. This leads us to the Runtime OS benchmark. This benchmark is not designed simply to measure how intelligent an AI is or how safely it can operate. What it evaluates is decision governance and accountable execution. To do this, we define 5 evaluation dimensions. The first is decision validity. This evaluates whether a finalized decision was truly valid in light of the objective, the available facts, and the applicable policies. The second is authority integrity. This evaluates whether the decision and execution remained within the correct scope of authority and whether all required delegation and approval processes were properly followed. The third is human gate fidelity. This evaluates whether situations requiring human judgment were correctly identified, whether the necessary information was presented, and whether the appropriate person actually reviewed or approved the decision. The fourth is trace completeness. This evaluates whether the entire process, from signal through decision and permit to execution, can be fully traced, including the reasoning and circumstances behind each step. And the fifth is fail-closed behavior. This evaluates whether the system safely stopped instead of forcing execution when it detected risks, policy violations, or uncertainty. So, the Runtime OS benchmark does not simply ask, what was the AI able to do? It asks a more fundamental question: can we truly trust the decision and its execution? By evaluating decision, authority, human gate, trace, and fail-closed behavior in addition to capability and safety, we can assess AI agents not merely as autonomous execution systems, but as systems that can be operated responsibly within an organization. And this idea of trustworthy execution is one of the most important principles behind Runtime OS. Finally, let's bring everything we have discussed in this video together into one concluding message. As we have seen, the capabilities of AI agents are advancing rapidly. They can reason, plan, use tools, and collaborate with multiple agents to autonomously execute increasingly complex tasks. But as AI becomes more capable, simply asking what can it do is no longer enough. Who finalizes the decision? What is permitted? How far should execution be allowed to go? When should a human be consulted? And who is accountable for the outcome? Unless these questions are clearly answered, we cannot confidently deploy AI capabilities within organizations and society. That is why the purpose of Runtime OS is not to create more agents or to build yet another agent framework. Powerful agent platforms such as OpenAI Agents SDK, Claude Agent SDK, AutoGen, and LangGraph can continue to serve as the operational layer. What Runtime OS provides above them is a decision infrastructure. AI and agents generate signals. Runtime OS finalizes decisions based on policy, boundaries, and authority. When necessary, it asks a human through the human gate. When execution is authorized, it issues a permit and allows the system to act. When an action is dangerous, uncertain, or exceeds its authority, the system stops. And the entire process, from signal through decision, permit, and execution, is recorded as a trace. In other words, act, ask, and stop themselves are governed by decision authority. We then evaluate whether this entire mechanism is functioning correctly through decision validity, authority integrity, human gate fidelity, trace completeness, and fail-closed behavior. Together, these elements form the foundation of Runtime OS. The goal is not simply to make AI more autonomous. The goal is to transform AI capability into trustworthy action through governance and accountability. Agent frameworks maximize the capabilities of AI, Runtime OS connects those capabilities to the right decisions and controlled execution. Capability X governance X accountability. Only when these three come together can we create trust. Runtime OS is not a mechanism for restricting AI. It is a decision infrastructure that enables us to transform AI capabilities into trusted value within organizations and society.